Hey guys! Today we're going to talk about performance in OpenGL. This is a pretty broad topic, but our focus is going to be the efficient usage of the OpenGL API. You see, OpenGL has been around for more than 3 decades, and over the years many people have pointed out the large number of API calls that you need in order to construct a single frame. This includes multiple calls to GL draw functions, as well as setting up all the uniforms and texture resources which the draw call depends on. Take for example the following scene which I've loaded in Blender. The scene is constructed from dozens of objects, and each object is accompanied by its own transformation matrix and materials. We can render the scene in OpenGL by loading the asset file using the Assimp library. If you're not familiar with Assimp, then check out the link in the video description. I have a full tutorial on how to use it. In Assimp, the scene is represented as an array of mesh structures. Each mesh contains its own list of indices and vertices, as well as an index into an array of material structures. The material provides details such as color, various textures such as diffuse and normal maps, and etc. In addition, the mesh can potentially point to a node in a graph, which organizes the objects using a parent-child relationships and provides transformation matrices which we need in order to calculate the position and orientation of the mesh in the world. So how do we render it? Well, the simplest way is to create a vertex and index buffer for each mesh structure. This allows us to populate the buffers with the indices and vertices of the mesh and render them using a call to GL draw elements. In between draw calls, we will need to bind the two buffers, calculate the WVP matrix and any other matrix which the shaders require, and also bind the textures so that the mesh is rendered using the correct material. This will work, but as I said, it's the simplest and probably least performant way there is. We can improve it by loading all the vertices and indices of all meshes into a single pair of vertex and index buffers and use GL draw elements base vertex as the main draw call. This function takes a base index and base vertex parameters, which can point to different locations in the index and vertex buffers. This means that we can bind our big vertex and index buffers once, and GL draw elements base vertex will take care of the rest. This is actually how I do it in my Assimp tutorial. However, we still need quite a few intermediate OpenGL function calls to handle the transformation matrices and the change in materials. Okay, before we jump into the solution, I'd like to say a big thank you to Marcin, who recently joined 3D Underground. If you too would like to support this channel, you can do that at patreon.com/OGLdev or by joining the YouTube channel as a member. Alright, the solution presented here is part of a larger effort with a very cool name approaching Zero Driver Overhead, or AZDO. It was presented already in 2014 by NVIDIA, and I will include a link to a GDC presentation for more details. The rationale behind AZDO is exactly what we've been discussing here. An excessive use of OpenGL function calls creates driver overhead, which limits the performance of the game. We would like to reduce the number of these function calls as much as possible. AZDO is actually a combination of several techniques. In this video, we will explore a core technique of AZDO called multi-draw-indirect. The idea is actually very simple. Instead of providing the number of indices and the base vertex and index to GL draw elements base vertex, we can create an array of structures with those pieces of information. A new function called glMultiDrawElementsIndirect performs a loop over this array and calls GL draw elements base vertex for each element in the array. We will see later on that there are actually more parameters involved here, so consider this to be just a pseudocode to demonstrate how this works. Now let's talk about how this array of structures gets to the GPU. You may think that we simply provide a pointer to the array in the host memory, and then the driver copies the data to the GPU. This could work, but it means that on every frame, this copy operation would take place, which might be quite an overhead by itself. We want to be able to handle a very large number of these command structures, so it would be better to put the entire array in GPU memory and avoid a copy during runtime. Therefore, indirect rendering provides a new binding point called glDrawElementsIndirect buffer. We can create an SSBO in GPU memory, populate it with an array of command structures, and bind it to the new binding point. When you're rendering static geometry, which is loaded once from an asset file and never changes, you can populate the SSBO once during the setup time and never touch it again. Okay, so by now you're probably thinking that this makes sense in terms of replacing the multiple calls to glDrawElements base vertex with a single call to the new API, but what about the transformation matrices which we may need and the different material for each mesh? How do we make state changes when we can't break into the GPU as it's traversing through the array of commands? The solution is simply to use an additional SSBO that contains more information for each mesh. For example, we can have an array of structures that contains the WVP, normal, and world matrices. Each mesh will have its own structure, and the system-maintained index of our position in the loop will take us to the correct element. Okay, enough talking. Let's see how to implement indirect rendering. Unfortunately, right now I don't have a simple example for it. I integrated a feature into my renderer, so I will show you how it works as part of a larger system. You can take the core idea and adapt or entirely replace the integration stuff for your own system. The main integration point is a class called CoreModel, which is based on the basic mesh class, which I've demonstrated in my Assimp tutorial. My rendering system also includes a scene class, which contains the list of objects to be rendered, and a renderer, which is a mechanism that sets up the different rendering passes, updates the shaders, traverses the objects in the scene, and tells each object to render itself. The idea is that the renderer is not exposed to the buffers in the object, and the object is not aware of the current shaders. The object, which is represented by the CoreModel class, needs to bind its VAO and textures and calls the draw function with the correct parameters. To handle the different transformations, there is a virtual callback function from the CoreModel back to the renderer that gives it the opportunity to update the shaders with the correct transformation matrices. Indirect rendering eliminates this process of going back and forth between the CoreModel and the renderer, but of course we need to set up the SSBOs correctly with the draw commands and the transformation matrices. Okay, so after this long introduction, let's actually see some code. I was able to implement the entire logic of indirect rendering in a new class called Indirect Render. So let's go over it and then see how it fits into the big picture. Let's start with the private attributes of the class. We have two handles for our SSBOs. The first one is going to hold the elements in the array with all the draw commands, and the second is going to hold additional information per mesh. It's called per object here, but basically the same thing. Eventually, every element in the draw command array corresponds to Assimp AI mesh structure. Now, technically, you only need the first one, the draw command buffer, in order to execute glMultiDrawElementsIndirect. But what I'm trying to do here is to show you how to actually make this useful, and for that you will need additional information which we have here in the second SSBO. So the assumption is that for every mesh we will need a transformation matrix from Assimp. As I said, in complex scenarios, Assimp provides a node graph with a transformation for different parts of the scene. And when we load an asset file using Assimp, we traverse the graph and calculate the final transformation for every object, or every AI mesh actually. So here we have a structure called mesh, which includes this transformation. And the reason that I'm using a structure here and not the matrix directly is because we're going to need a material index, but I'm leaving this to the next video. So here we have a vector of meshes, and this vector will include the transformation of all the AI mesh structures from Assimp. This vector, of course, will go into the second SSBO, and we will see later on in the Vertex Shader how to pull the transformation for the current mesh or the current element in that loop for the glMultiDrawElementsIndirect. We have a few private methods here, but we will see them later on when we get to the CPP file. So in the public section, we have two functions. The first one, init, is called once when we set up the indirect render. And the second one is for every time we render a frame. The init function takes a reference to a vector of a basic mesh entry structure. Now, what is this thing and where is this vector coming from? So to understand this, we have to go to the CoreModel class. As I said, this class is based on the basic mesh class that we saw in the Assimp tutorial. So I'm not going to go over this thing, it's very big. You should simply watch the video on Assimp. But what you can see here is that we have a vector of the basic mesh entry structure. Now remember that before we had indirect rendering, we used to traverse all the meshes from Assimp and issue a glDrawElements base vertex for every mesh, for every AI mesh. And this function needs the number of indices and the base vertex and index. So when we load the asset file, we populate this vector, and this structure contains all the information that we will need to issue the draw commands. As you can see, we have the number of indices, the base vertex and the base index. We also have the number of valid faces and the material index, which we will not need in this tutorial. So when we initialize indirect render, this vector should already be populated, and so we provide it here as a reference to this function. The render function takes a transformation matrix called object matrix, and the idea is that in addition to these transformations, which are basically static, they are calculated when the asset file is loaded. The user may also provide a transformation during runtime. For example, if he wants to move the object or change its orientation, rotate, scale it, or whatever. So this transformation is already known when this class is initialized, and this one is dynamic, provided during runtime. So now let's jump into the init function. We start by making sure that the meshes vector is not empty, and then we initialize our own internal vector of meshes, and after that we initialize the two SSBOs. So the init meshes function is very simple. We're basically going to copy the transformation from the parameter. So to do that, we initialize the private vector using the size of this parameter, and then we traverse the vector of the basic mesh entry, and we simply copy the transformation into our private vector. And I prefer to copy the information instead of simply maintaining a pointer to the original, because I prefer to avoid keeping links from this class to the caller, but you can do this whatever way you see fit. Next, we initialize the SSBO with draw commands, and this function also takes the meshes vector. What this function does is to create a buffer handle using glCreateBuffers. You can see we provide the address of the draw command buffer handle, and then we populate it using glNamedBufferStorage. Okay, this function takes the handle of the buffer, the size of the array. So for that, we take the size of the first element and we multiply it by the number of elements in the array and the pointer to the start of the array. This array is, of course, a vector of the draw commands. So if we take a look at the documentation of glMultiDrawElementsIndirect, we actually see the definition of the structure for the draw commands here. And the funny thing is that this structure is not part of the OpenGL API, as you would expect. I mean, to avoid mismatches between user code and what the GPU is doing, I would expect this structure to be part of the API, part of the headers, because the GPU is going to follow this specific definition. Okay, so for example, the count is going to be at offset 0, and then the instance count is at offset 4, first index at 8, and so on. But unfortunately, this is not the case. So what you need to do is to copy this structure into your code and make sure to keep it exactly like that. So you can see that I copied this structure into the top of the CPP file right here. And now what we need to do is to resize the drawCommands vector for the number of meshes, and then traverse the meshes vector and initialize it. So the good news is that we already did all the calculations in the CoreModel class. So now we just need to copy the elements. Okay, so the draw command has a count attribute, which is basically the number of indices, and we have that. We're not going to use instances in this case. So the instance count is 1 and the base instance is 0. The first index is what we call the base index. And we also have a base vertex, which we also have in our basic mesh entry. And now that the vector is fully populated, we can copy it into the SSBO. If we jump for a second to the CoreModel file and search for glDrawElements base vertex, you can see that this function uses the same information, okay, the number of indices, the base index, and the base vertex. So the first SSBO is ready, and we need to allocate the second SSBO, which is down here. This function only allocates the SSBO, but it doesn't populate it, because this will be done during runtime. So we call glNamedBufferStorage just to prepare the memory for it. In this case, the size of the SSBO is the size of a structure called pairObjectData times the number of meshes. This structure is also defined up here in the CPP file, and it contains two matrices. We have a world matrix and a normal matrix. And this is because this is what my Vertex Shader requires, so in your case it may be a bit different. We will see the Vertex Shader later on, and then you can think up what you actually need to do in your case for this structure. Since we're not populating the SSBO at this stage, we provide a null here, and we have something different in the last parameter compared to the previous SSBO, because the data for the first SSBO is basically static. We are not expecting this vector to change, right? The number of indices, the base index, and the base vertex are always going to be the same. And therefore, the last parameter of glNamedBufferStorage is 0 because we're not passing any hints to the system here. In the case of the second SSBO, because we expect this to be dynamic data, we provide a hint for that to the system, and this is the glDynamicStorage bit. Now that the two SSBOs are ready, we can go ahead and render the object. Remember that this class only deals with the issues pertaining specifically to indirect rendering, so handling the VAOs and whatever is still being done in the CoreModel. We will see this later on. So the render function, as I said, takes a transformation matrix for the current frame. So we start by updating the second SSBO using the matrix, and then we bind the first SSBO, the drawCommands buffer, to the new binding point, glDrawIndirect buffer. And then we call the new function glMultiDrawElementsIndirect. The first parameter is as usual the topology, and I'm using triangles. The second is the size of the indices, and since we're using 4 bytes per index, we have unsigned int here. The third parameter is a void pointer called Indirect, which specifies the address of a structure containing an array of draw parameters. And this is of course the contents of our first SSBO, and this parameter simply allows you to provide an offset into the SSBO, just in case you have different types of data inside it, and the drawCommands vector doesn't start at the beginning. Our vector starts at the beginning, so we have null here. We don't need that. The next parameter is the number of drawCommands that we have. So of course this is the size of the meshes vector. The last parameter is 0. This, as you can see, is called a stride, and the idea is that it specifies the distance in basic machine units between elements of the draw parameter array. So the idea is that the draw commands don't have to be consecutive. Inside the SSBO, you can actually add some padding between them. And if you do that, you will need to put the size of the padding in bytes into this parameter. We of course don't do that, so 0 in our case. After the draw command, we disconnect the SSBO from the glDrawIndirect buffer binding point. So now let's see how to update the per object data. Again, this code is very specific to my implementation. So you may find it useful or you may need to change it completely. What I'm doing here is to define a vector of the per-object-data structure. Again, this structure contains a world matrix and a normal matrix. We start by resizing it for the size of our internal meshes vector, and then we traverse the vector of meshes, and for each mesh, we calculate a final world matrix. This transformation is the multiplication of the object matrix, which is the dynamic parameter, by the static transformation of the current mesh. Okay, so first of all, we apply the transformation that comes from the Assimp node graph, and then whatever transformation that comes from the game itself during runtime. And this matrix goes into what is called the world matrix. The normal matrix is the transposed inverse of the world matrix. Okay, so first of all, we inverse the world matrix, then we transpose it, and this provides us with the transformation that goes into the normal matrix. Okay, so this is standard calculation of a normal matrix. Once the vector has been populated, we call glNamed buffer subdata to update it into the per object buffer, the second SSBO, okay? We provide the size of the vector here, and I'm actually using a macro here called array size in bytes, which does the same thing as what we saw here. I should probably use it here as well, but whatever. And a pointer to the beginning of the vector. Next, we need to bind the SSBO. But since this is a standard SSBO, we call glBindBufferBase, and the binding point is glShader storage buffer. Okay, this one was glDrawElementsIndirect buffer, and this one is very specific for elements of the draw commands, this guy. This one is a generic SSBO, and because it is generic, we also need to specify a binding point, because you can have multiple SSBOs, right? So I have a file which is kind of like a database of all my SSBOs. The first one is for the vertices, because I'm using what is called PVP, Programmable Vertex Pooling. I have a tutorial on it, check it out. So our per object data is going to be in the second SSBO. We have more SSBOs here for the material and the diffuse and normal maps, but we will see those in the next video. So ignore them for now, we're only using these two. So this is our binding point, and this is the handle of the SSBO. Okay, and then the render function continues as we saw. So now let's see how to use this class. So we go to the CoreModel class, and you can see that I've included the glIndirectRender.h file, where the new class is defined. And then in the CoreModel, we have a new attribute of the new class. So let's jump into the CPP file and see where it is used. So at the end of the init geometry function, we see a call to the init function of the indirect render member. So this function takes a vector of the basic mesh entry structures, which is updated early in this function by count vertices and indices. Okay, you can see that this function updates the vector with num indices, base vertex, and base index. So when we get here, this vector is fully populated. Notice that this function is only called if the useIndirectRender flag is set to true. And this is simply a global Boolean flag that allows me to enable and disable indirect rendering. And the reason that I'm doing this is to enable debugging, and also because I want to maintain backward compatibility with the latest code for the previous tutorial that didn't use indirect rendering. If you plan to only use indirect rendering, then your code, of course, will be cleaner. The next usage is, of course, the call to render. So I have a new public function in this class called RenderIndirect. Previously, I had a simple render, which traverses the meshes vector, calls renderMesh, and then we call glDrawElementsBaseVertex for every mesh. But RenderIndirect is much simpler, of course. So what we do here is simply to bind a VAO. If programmable vertex pooling is enabled, we also need to bind the vertices SSBO, and then we call render on the indirect render member using the provided object matrix. So this of course takes us to the method that we just saw. After the call to render, We disconnect the VAO as usual and go back to the renderer. The last thing that we need to go over are the changes in the Vertex Shader. And I'm actually going to use the Vertex Shader that I'm using for skinning simply because the demo is a bit more interesting in this case. First of all, we have a new uniform variable called isIndirectRender. This is a Boolean flag which indicates whether indirect rendering is enabled. As I said, I want to be able to enable and disable it at runtime. So by default it is false, but you can enable it on the application side. Next we have the definition of the SSBO for the per object data. This is a read-only buffer on binding point 1. Okay, make sure the application side is synchronized with the Vertex Shader. The contents of this SSBO is an array which of course matches what we have on the application side, okay? So this structure is specified in GLSL, but it's the same thing, a world matrix and a normal matrix. Both are matrix 4, or a 4x4 matrix. Now let's see the main function. We start as usual by calculating a bone transformation matrix, and we use it to transform the position. Okay, so this is a common code for both direct and indirect rendering. Then, depending on whether indirect rendering is enabled, we do this part or this one. So this is basically the old code, the direct rendering path. Okay, calculation of GL position using the WVP matrix, and then a transformation of the normal, tangent, and bitangent, and then calculation of the world position using the world matrix. In the case of indirect rendering, we calculate GL position as follows. We start from the local position, same as this guy, and then we pull the world matrix from the SSBO for the current mesh. And to do that, we have a system-generated variable called glDrawID. This variable basically tells us our position in the for loop over all the meshes. Okay, remember that the GPU will automatically traverse this vector of draw commands. So glDrawID corresponds to the index of the current command, and we use it to access the array in the second SSBO, the per object data. Okay, O is the name of the array in this SSBO, which has a world matrix and a normal matrix. So we use the world matrix to transform the local position, and then we multiply it by the view projection matrix. Okay, usually in the direct rendering case, we have a combined WVP matrix, a world view projection matrix, so we can do this transformation in one go. This matrix is updated before the draw call, so it already includes the current world matrix. If you want to maintain the same calculation as the old one, you can simply multiply the world matrix by the view projection matrix and change the name for it, and then you'll have a single multiplication. This can also work. Next, we use the same logic to transform the normal, tangent, and bitangent vectors. It's just that instead of the world matrix, we use the second matrix, the normal matrix. And finally, we calculate the world position using the world matrix. So actually, if you want to use the same logic, you will need a world matrix, a normal matrix, and a WVP matrix. That's it in terms of the specialized code for indirect rendering. The handling of the texture coordinates and the calculation of the light space position is the same for both cases. Now let's try to run this. And this seems to work, except that we don't see the material of this character. If we disable indirect rendering for a second, we can see that there is actually a material here. So the reason is very simple. If we take a look at how we render a single mesh, we can see that the mesh's vector contains a material index, and this index is used to access the material's vector, and then we can bind a diffuse texture. We can bind all the textures of all the meshes to different texture units and include the index of the texture unit in the per object data. The problem is that texture units is a limited resource, and in the case of a complex model, it's quite common to run out of texture units. Also remember that each mesh may include a diffuse texture, a normal map, and more, especially in the case of physically based rendering. So this brings us to the next topic in AZDO, which is bindless textures, which is of course the topic of the next tutorial. So thank you for watching, and I will see you next time.